Hello, I'm Tom Hollingsworth, and this is Networking Field Day 13. We are here in sunny Silicon Valley, California, with SolarWinds. You are about to watch a presentation featuring SolarWinds and their unique solutions and products, along with a group of delegates around the table who represent the best and brightest in the networking industry. They have been invited to ask questions, make comments, and offer their opinion, and represent the networking community at large. If you would like to know more about Tech Field Day, including how to become a delegate or how to become a sponsor of this event, please go to our website at techfieldday.com. If you would like to see more videos like this about a wide range of technology subjects, please check out our YouTube channel at youtube.com/techfieldday.
Okay, ready to talk about how Netpath works? Okay, so the first question is the sort of the mental model here, and the easiest thing to compare to is Traceroute. So that's what we're going to use. Do you guys know how Traceroute works? You guys think you know a little bit, or experts, or who wants to commit? No one wants to commit to being an expert. You guys know what Traceroute is?
Yeah.
Yeah. You can't say you don't know what Traceroute is and be at Network Field Day, can you? Okay. So I'll talk a little bit about Traceroute.
If that were the case.
No one said they know how it works. We'll use the whiteboard here, and this will help us understand. So what we'll do is, like, we actually started when we were building Netpath by using Traceroute. We actually just used Traceroute, and we ran into sort of naturally a bunch of limitations that we had to work around. And eventually, like, Traceroute did not work, and we tried some sort of exotic forms of Traceroute, and that did not work either, and so we built our own stuff. And so I'll talk to you about a little bit how Traceroute works as a path, or as a way to understand how Netpath works, the problems we ran into, and what solutions we put in place. Okay, so we're going to take an example network, and I'm going to remind myself to write big. So on the left-hand side, you have your source, right? We use the same symbols and everything. We connect to, let's say, R1. That connects to R2 up top. We'll have a destination over here. Maybe across the bottom there's multipath. We'll have R3, we'll have R4, R5, and these will all connect together like this. Simple enough, right? Okay, so when you're at your computer prompt, bloop, and you type in traceroute, traceRT, whatever, and where do you trace to? You trace to 4.2.2.2. That's what we all trace to. What happens here, right? You send a packet, generally an ICMP packet, over like this. You craft it to this destination that you specify. You put in a TTL of 1. You guys know what TTL is, I hope, I expect? Time to live. So when this thing gets to 0, the packet throws it away, or the router throws it away. So you send a TTL1 ICMP packet, makes it to R1. R1 says, I have to route this packet. I'm going to decrement TTL from 1 to 0. Packet is now dead. I throw away the packet. So loop avoided, right? That's the point of TTL, is to avoid these loops. Loop avoided. Now after that, R1 says, okay, I threw away that packet. I should totally tell the source that I threw away their data, because my job is kind of to send their data. So he crafts his own packet sourced from R1, and a little tidbit for you. This is always the ingress interface of this packet. He sends that back to the source. So then on your little prompt here, you see that hop number 1, TTL1, we have R1. You'll see his IP address, and then generally it'll do reverse DNS lookup, but for the sake of writing quickly, you'll see hop 1 is R1, and specifically this interface's IP. Make sense? Everyone knows this? Cool. Okay, then we do it again for hop 2. We send TTL, and technically we do this 3 times, right? And we get a value here, so maybe this is 2 milliseconds. So we send 3 packets like that, and they're when we time the difference between when we sent and when we received that packet, that's our time that we see, right? Okay, so the next thing is we send TTL of 2. So we may go like this. R1 decrements 2 to 1. He goes ahead and routes, picks through his load or ECMP or whatever he's using to pick the route, picks this top route. He receives TTL of 1, goes to 0, because he has to transit this way, throws away the packet, creates his own packet and sends it back, right? So now we know about R2. Okay. We have some latency. Let's call that 5 milliseconds. Cool. Okay, so that's how it works. Now, the first problem we run into is we do this at SolarWinds Office and it doesn't work and stops at our firewall. And this was like a wake-up call that most organizations, or at least many organizations, just block this ICMP traffic. It doesn't look like application traffic. So security best practice is allow what you need and then block everything else. No one is sitting at their desk needing ICMP except us lowly network engineers. So oftentimes that is blocked. Block it at SolarWinds, so we were stuck. So the first thing we ran into is the firewall blocks, and the first solution was, so we thought about it and we were like, why is it being blocked? And we sort of had this realization that really guided our development from that point on, which is just act like the application. Like, what's the network truth here? The truth is that we're being blocked because we look like we're something different than everything else, which is also why ICMP gets different performance than everything else. So pretend to be the application, and then you will get like performance, you will get through firewalls, all of these sorts of things. So we made our traffic TCP traffic and otherwise emulated the application. So then suddenly you get past your firewall and you can see the rest of the path, okay? So that's the first problem and the solution for us. The next problem is path mixing. So I talked about up through the second hop. Let's see the third hop. Now the issue here is that there's no relationship, sort of the traceroute implementations don't keep a relationship between these packets. They're all separate, right? So when you send this TTL3, it goes to the first one. Maybe R1 elects to send to R3. So TTL decrements from 3 to 2, from 2 to 1, and then from 1 to 0. So now we stop at R4. So nothing changes about our process here. We write R4 just like your system would, and we start putting in numbers for the latency. Okay, that's weird because R1, R2, R4, that's no path, right? You're trying to discover this topology, and this is not any path on here at all, right? And so I think a lot of people are not aware. I'm curious, how many of you actually knew that was occurring, this path mixing stuff?
You usually see, like, if you have a split in the path, I'm used to seeing R2, R3, R2.
Yes, so if there's 3 packets sent by default, whenever you get multiple IPs, this is the reason why. The challenge is when you go past that, for example, as we are here, then there's no correlation. So then you can get your third hop on this side to be R4, and your third hop on this side to be R5, and then your fourth hop will be R5 in the destination. So then you start mixing them at different TTLs, and it gets, I don't know how to parse that. Looking at those, I don't even know how to parse that. So this path mixing is something a lot of people don't realize, and it's kind of like Traceroute's lying to you. It's really confusing when you have this going on. Okay, so how we solve that is something we call distinct path. So every time we discover a path, we control the data in our packets such that we take the same path, right? We know how these routers select their egress interfaces, so we control that information, we test that information, we make sure that we've got a consistent path before we pull that into our data set. Okay? All right, so that controlling of the traffic that we send and the testing of it, that's how we make sure the path mixing is fixed.
So Brian, you're seeing this because of equal cost multipathing, right, in the backbone?
We're seeing this because of multipathing, yes. Not always equal cost, but yes.
Okay. So I mean, how are you? Most networks don't honor source routing. So how do you validate that are you just sending so many probes along these paths that you're able to discover both of them?
Yeah, we send a lot of probes. That's a piece of it. And then all different routers have different mechanisms for electing or selecting their egress interface. So we abuse that information to try and push them to select multiple egress interfaces. Okay. And the next thing is control plane performance versus data plane performance. So when you send these packets, and it sort of differs by the hardware platform, it's very hardware specific, but when you send traffic through R1, generally that traffic is transit traffic. That's 99.9% of R1's life. I receive traffic here, I send it out here, I do sort of my changes in encapsulation, I look at my fib and all this sort of stuff, and I just fast path that traffic through, right? And that's R1's almost his whole life. That's data plane, right? Now when you send one of our packets, or one of the Traceroute packets rather, it goes to R1, R1 throws away that packet, and it punts that process to the CPU, right? Because this is no longer transit traffic, this is some sort of anomaly. We're going to use a generic CPU rather than application-specific hardware, ASICs, to do that. So it punts it to the CPU constructs the response packet and sends it. And what that means is the performance of your test traffic is different than the performance of your transit traffic, even regardless of any sort of QoS or any mechanism like that. Okay, so that's a big problem. And how that looks like in your trace is, you guys may have seen this, you'll see something like, R4 is 77 milliseconds, and then your fourth hop, which is R5, he is 6 milliseconds. So where's the problem here, right? When you put this in front of most network engineers, they will tell you, aha, I found the problem. It's that 77 milliseconds. It's the highest number, which makes sense. But we can see that if our transit traffic can pass that point in the path, assuming that we've already fixed path mixing, if it can pass that point in the path and get good service, then transit performance is fine, right? Then that's not a problem. Then if your CPU is loaded up on this device and it's responding slowly, maybe you want to look at that to keep your network healthy, but it's not a performance impacting problem, and it's not something you need to worry about when you're doing a trace, right? Okay. So that's, okay, so how we solve that, sometimes I forget this to specify the solution. So how we solve that is we're very cognizant, there's a lot of control of the path, and once we reach past the node that's providing, so when we get the response from R1, that's his response, transit all the way to him, inclusive of his control plane delay. When we get R2, if it's through R1, then we know that's transit through R1, exclusive of his control plane delay, and now inclusive of R2's control plane delay. So knowing that relationship, we sort of put all of this data together across potentially hundreds of probes and paths and sort of merge it so we can come to a good conclusion about what is the transit delay for R1. And that's what all the numbers are when I show you in the demo. Always transit delay. Okay, so we talked about firewall blocks, path mixing, control plane versus data plane performance, and these are all the reasons we ended up having to write our own. Okay, so we wrote our own probing algorithm. We construct our packets. We use a packet driver WinPcap to do that and listen to the responses and parse and then interact with that. So sort of if we get certain responses, we know how to send our next probes and so on, right? So does it make sense, sort of the basics of how the probing works? Because we're going to add layers on top of that now. Okay. All right, so the next thing is determining status, aka chasing the network truth. So again, this is sort of this idea of what is the network truth here? There's really challenging stuff we have to solve, and sometimes we don't know how to solve it, and we have to remind or think to ourselves, the answer here is we're trying to get at the network truth. What is the network truth here? So the first example is a threshold problem. So we sort of showed the graph that we have and the demo that we have to some users. And initially, when we were just discovering and showing the numbers, and they were like, "Oh, that's cool, but where's the red?" Initially, we were actually coloring autonomous system numbers with the colors that define the color. And so they were like, "Well, red should be the bad thing." And we're like, "Right, okay." So we kind of did do that through the last 10 years of all of our other products. So now we realize we have to present not just a whole bunch of data, we have to present an intelligent conclusion. And how SolarWinds does that is we say something is green, red, or yellow. So now we have to figure out how to take this huge data set that we have and translate that into red, green, or yellow every spot every sort of element that we draw on the screen. So how we normally do that is thresholds, right? That's how you normally decide red, green, and yellow. So the problem with this is when you have these paths, we're trying to determine where the problem is for each component. So when you take each edge or link or connection is unique, a unique pairing of, for example, R1 to R2 is a unique edge, R2 to R5 is a unique edge in graph theory. When you take all of those and then you add all of the nodes, you think, okay, so I have to set thresholds 100 times, 200 times on this picture. That's not a fun way to spend your afternoon. And by the way, it's the internet, right? So all of these nodes move and change all the time. So it's unpalatable. Like that's not you can't do manual thresholding on this in a way that makes sense. We did try anyway. We tried to make it the largest number, and then we would just draw red wherever there was a WAN link. So that was dumb. So when we think, like, what's the network truth here, we have to think deeper. So if you see a picture like this, and this says 5 milliseconds, and this says 500 milliseconds, which one's unhealthy? Anyone? Any thoughts? There's no good answer, right? Like there's not enough information to provide a good answer. It's an unfair question. But basically, like you don't know just from that number what's unhealthy or what's not. If this is a LAN link, if this is a cable between two devices in the same rack, that's kind of a high number. Whereas if this is a satellite connection, it's a good number, right? So just that number does not define unhealthy or healthy. So we have to come up with a better way to do that. And so how we did that is this concept we have of unhealthy latency. We have, so we're very fortunate to sort of stand on the shoulders of the QoS guys who figured a lot of delay out. And QoS guys will tell you that delay comes from 4 different sources. When you receive a packet, you do processing, you do queuing. If you have QoS, even if you don't, you at least have a FIFO queue, right? Your data sits in a queue for a while. You do serialization. So when you're sending data across a wire, at some point it has to become voltage spikes and decreases, right? You have to translate that, and that's serialization, or waves if it's fiber. And then the last one is propagation. So the I hope I'm spelling that right. So the packet is received, CPU, ASICs, whatever, have to do some processing. It sits in a queue for a little while. You turn it into voltage or light. That light flows across a physical medium, a wire or a fiber cable for 5 meters or 500 miles, whatever it may be. So all of the data, all of the delay in networking comes from those 4 sources. Right? So the next thing we ask ourselves in analyzing this, we see a couple of things jump out. One is propagation delay is based on physics. Light and voltage only moves so fast. So this one is generally not where bad behavior comes from. This is not something that increases due to bad behavior. Make sense? Serialization was more of a concern when we had ISDN and we were trying to send voice over it. Today's network serialization is such a small number that, again, it's finite, it's controlled, it's not where unhealthy latency comes from. Queuing is where unhealthy latency comes from. If you've got big queues because you're prioritizing your VoIP and your other traffic is waiting, it will impose some delay on your traffic. And certainly processing, if your ASICs or your CPU is too busy, can be a source of bad latency. So what you have here is you have bad latency and good latency. And since propagation delay, in modern networks, these top 3 things are all intended to be extremely, extremely fast. So the biggest component is generally propagation delay, and usually on a WAN, right? To get across the US, it takes, 30 milliseconds, right? So the next step is easy, right? We have to identify which delay, in every time we draw a number like this, 5 milliseconds, 500 milliseconds, we have to decide, is that delay coming from here or here and how much? And so we do that. We break it out and that's what we call unhealthy latency. And then when we have a 500 milliseconds that we display in the front end, on the back end, we know that 20 out of 500 milliseconds is unhealthy.
A marker that might show up a little better up there.
Try another one.
It's starting to fade.
I love a good, look at that one.
good.
I should use that one from the start. I love
Juicy.
a good marker, whiteboard marker. Okay, so this ratio between these two numbers, that's how we determine degree of unhealth link by link. So now when we have our topology like this, and these guys are in the same building and these guys are in the same rack, if he goes up to 10 milliseconds, while he's still 500 milliseconds, then that's healthy for a satellite link, we can color this as red because it's the unhealthy thing. Cool? Make sense? Okay. So that's...
All right. So how are you determining that, though? Is it just through baselining, or?
No, we can't use baseline. Like, that's what we tried to do when we started. We used baselining, algorithms, linear regression, all sorts of stuff for our traditional product. The problem here is we want this to be a troubleshooting tool, which means it has to work on the first interval. And if the problem is ongoing, you can't just say, oh, well, that's my baseline, so it's fine. Okay, so we had to come up with another solution. So this is sort of the first half of the solution, and the other half I don't want to share yet.
Okay.
Wait till the rest of the patents are pending.
Fair enough.
But this is for an explanation of how we thought about it and how we're coming up with the red and the green for each one of these. Okay. The next one is packet loss or packet delivery. So when the source attempts to connect to destination, let's say this is Google. Oh man, that is a good marker. When you go from source to destination of Google, he has to first resolve, do the DNS resolution. He has to send the traffic through, and then there can be just an uncountable number of reasons why that packet does not make it to the application. Okay, and so we have to measure all of that because we want to know what the transit is all the way to the application. Okay, so I'll give you some examples. If the packet, if he can't resolve Google, do we call that packet loss?
No.
He didn't even send a packet. So the source didn't even send a packet, so how can we consider that packet? That's definitely not packet loss, right? That's definitely not packet loss. What if we send all the traffic through, it makes it to the destination, we receive a response from the destination that that port is closed? Then the network is not dropping any packets. In fact, we know for sure that we are providing good transit, but the destination is dropping the packet before it hits the application. Is that packet loss? I don't think we should report that as packet loss. That's something else, right? Last one is, what if you have a routing loop? And I can show you how this looks in Netpath. What if you have a routing loop, right? This traffic transits this link many, many times, and generally how you measure packet loss is you measure how many times do you transit versus how many times do you drop it during that transit. So if he loops through here 30 times and he drops on the last one, that's not 1 out of 30 or 1 out of 31 packet loss. That doesn't make any sense, right? So we had to come up with this other concept of packet delivery. What percentage of my packets am I delivering? And so we take traditional packet loss where we've gotten packets to R1, but they don't get to R2 at a rate of 20%. We've taken the DNS resolution failing sometimes. We've taken routing loops, taken all of this data set, the port, all of that stuff to present you a number of what percentage of your traffic is actually making it, is being delivered. Okay. So the next thing is component versus, these are all hopefully this is making sense to you. These are all little nuggets, and then we'll talk about how it all comes together in one picture. Little nuggets of things we had to solve. The next one is component versus path and transit likelihood. So again, using this example, let's say that we have this link takes 1,000 milliseconds. Actually, I'm not that good at math, so we're going to start with some fresh new numbers, otherwise I'll just get confused. The relationship between these numbers is definitely important. Okay, so let's say this is a quick link. This one takes 250 milliseconds. This one takes 120 milliseconds. This is 5 milliseconds. This is 5 milliseconds. When we are trying to present the user with an intelligent conclusion of where the problem is, and we know this is unhealthy and this is unhealthy through this mechanism we already discussed, which one of these two are more unhealthy? That's another trick question, of course. So the degree of unhealth that you want to present to the user is how much impact does that have to the service from the source, right? So if this thing is taking up, is being used by 5% of my traffic, and this is being used by the other 95% of my traffic, then we definitely want to draw the red here and focus users in on here, right? Because even though it's less severe of a problem in terms of that component's performance, is more severe in terms of the end-to-end performance. Makes sense? And it's not easy to, or it's not hard to calculate that out. You multiply it all out. It gets harder when you're trying to aggregate all of the different graphs together, all the different paths. So that's component versus path and transit likelihood. And you saw transit likelihood was sort of built into all the visualizations we have. The next one is completeness for diffing. So when you have this and you can discover this most of the time, that's great. And then when you build a little graph, you're stupid, and you build a little graph like we did at the bottom, and now people can click these values, then my expectation is when I'm sitting at this guy and I click the next interval and I load that graph, if I see a new router pop up, that was a route change, right? That's the expectation from the user. So diffing imposes a much more sort of a larger demand on the system to be complete. We need to know about all of these nodes for every interval. Otherwise, we will present to the user that you're having routers added and removed every time. Horrible problem, very painful. So we came up with an algorithm that's basically, as we are getting all of these paths, we can determine a point at which we're complete, and then we can stop probing. And so that's why you have to be careful of, do I provide the probing 10 minutes? Do I provide 2 minutes? Because you need that completeness. Otherwise, you're going to see this top piece, and then you'll see the bottom, then you'll see the top, and so on. Now, the good thing is we can actually the algorithm we've developed specifies or predicts the percentage of completeness. So now this is an arbitrary value in the database we can change whenever we want and say the goal right now is 95% completeness. That's working pretty well. We could make that whatever number we want it to be. Okay, what's next? Okay, so we're going to do this slide in reverse order, so it's more fun that way. So we've got this distributed architecture. We have an agent. The agent does the probing, reports results back to the poller. Poller writes to the database. Web server presents it to the user. That's the basics of it, right? When we do the agent deployment, that happens within our application. We put out this little agent, sort of agent framework thing. And then we have plugins for all the little things we want that agent to do. One of the plugins is the Netpath plugin. So we deploy the Netpath plugin next. And then we do the plugin configuration. Hey, you need to go monitor www.google.com. Probing happens, which we just described. Hopefully you guys mostly understand the probing. Initial analysis happens as we do the probing so that we can adjust to what we're seeing and continue to probe and get the best data. And then sort of compress that data a little bit based on what we need and report that up to the poller. The data, after it's reported to the poller integrates data from other data sources and does additional analysis, additional sort of munging on that data based on that additional data set it has at the poller, which is all the other data in our other tools. Poller stores the results in the database. When you do your clicking around on the web interface, it presents the data, and that includes sort of a final layer of an analysis before we present it to the user. So end to end, that's how Netpath works. Any questions about that? Does it make sense? So when we talked about it in February, there was a ton of questions about how it works and sort of what we're doing like Traceroute or not like Traceroute. So hopefully this sort of provides clarity around that. Let me know if you have any questions that you're thinking up as you go along. Another big step here is data integration. So we do, at the Polar, we do go and query some internet databases. REARs are an example of one. We thought this was going to be a really easy thing, so we were like, this is a public resource, and we'll just query it whenever we need it. That was followed by like a huge number of queries. We quickly got banned from using their resource, and we've got all of these different IPs for this office and that office, so we're like jumping around trying to get access and continue developing. We eventually got honest and called them up and said, hey, you guys have a public resource, we're trying to use it, make it more valuable for users, but it turns out you don't have infinite compute. So what do you want this to look like? What are the limitations? And we had to spend a lot of time, much more time than I would have liked, working on how we do caching and throttling and all of these things so that we can be a good network citizen and use these resources and present that value to end users without just crushing these database servers. We take that data and enrich the path with it. So that's when you see the name of the networks and their email addresses and phone numbers if you want to contact them. We also do ingress-egress port mapping. So hopefully you guys saw that. So when we are looking at a path and we find these different nodes, we may also be monitoring those nodes in one of our tools. And when we are monitoring those nodes in one of our tools, we know we have a lot more data about that node, right? So we pull that into the graph where it makes sense to highlight issues. I call them issues, the little sort of bullets that come up here. Actually, let's look at Tableau. We call those issues, and we can see that sort of like this is a router that's shown right here. This is not a multi-layer switch. It's not a firewall. It's a router. It's a Cisco 2621. If we click and click over, that will take us to all of the data that we have about that specific node. We'll wait for that to load, and we can do the same thing with interfaces. So particularly when you've got multipath, this interface sort of mapping is very important to be able to see its metrics right there and then also drill down into the deeper view if it loads.
That's really great info. I think I'd like to see it on the display, having spent some frustrating time working with a competing path product where I had to keep drilling down and clicking around to just find the name of the interface or what speed the interface was operating at, stuff like that.
Yep.
So, flyover is good. Putting it on the graph is even better, I guess would be the feedback.
Yeah, I mean, I think we're fortunate in that we have this huge set of data we've been developing over a decade. So it's really, all we had to do is map it, right? We just have to map that out and make sure that mapping is accurate. And then we've got it all and can incorporate it into the graph.
Good stuff. Ease of use is the key here, I think.
Yeah.
Too long we've been, tools have been squirreling away information, but making people work to get what they need to solve a problem.
Yeah, yeah. I have been sitting there and looking at the walls of syslog and the walls of alerts, walls of you've got a power supply out. I don't care about that right now. So yeah, the impact is what was our driving goal here. Okay, so we talked about ingress-egress port mapping, and we enriched the path with that data, and finally root cause. So when we're aware of an alert on an item, when we're aware something's over threshold, CPU is high, interface bandwidth is high, RAM is high, all sorts of different things we already detect, we will add that as a call out, a textual call out on the screen with these, which you saw with a config change, when there's a performance problem at that node. So again, trying to correlate and simplify the picture.